So this talk is going to be a slight deviation from lots of the things that we have seen in the last couple of weeks here. In that it's about multi-view feature learning. That is, we're trying to do feature learning in a way that goes beyond object recognition, basically. A few buzzwords to characterize the things that I'm going to be talking about in the next 2 hours in the 2 parts of my talk is things like bilinear models, mapping units, energy models, complex cell models in relation to what Thomas has been talking about at the end of his talk, spatiotemporal features, gated Boltzmann machines, quadrature features, and stuff like that. But the punchline is basically how can we utilize feature learning ideas and deep learning ideas to do things possibly beyond just object recognition. Okay, so one could argue that object recognition is sort of the holy grail still of most of the applications of feature learning models and deep learning models. That's where these deep learning ideas really shine, what works really well in practice. And so I'm going to spend just a few minutes, like a couple of slides on object recognition, just to then set the stage for the ideas that are going to bring us beyond that topic. So object recognition started to work very well a couple of years ago in the vision community, and the main reason that that it started to work is basically that people started to look at local features, right? So you crop little patches from your image and try to represent them in some way, and in doing so you get around problems like occlusions and other invariance problems. And basically, local features are what made object recognition work well. The two complementary main approaches, as you all know very well, and have seen lots and lots of times in these in the talks in the summer school, is one of them is bag of features ideas, right? So you find interesting points in the image using something like Sift key points, Harris corners, something like that. Then you crop patches around those potentially interesting points, and you represent each patch using a typically very high-dimensional feature vector, and at the end you just add them all up, or build a histogram, or do something like that, so that you get a descriptor for the whole image from those local descriptors, and that then is something you can plug into some classifier, and that's going to tell you that on the image what you see is a cathedral, for example, but which particular one. But so the key ingredient, of course, is the local features that makes this work. The other complementary approach to that is convolutional. So you can, rather than finding interest points and so on, you can just scan over the image, crop all the possible patches, overlapping, non-overlapping, whatever you prefer, and again represent each one of them with a local descriptor. And rather than adding them all up, you can also concatenate them into an even larger vector, which you then again plug into some SVM or your favorite classifier, and then you have an object recognition system that's going to tell you which object you see in this image. So both of these approaches can also be combined, of course. You can do a little bit convolution in parts of the image and then add up all the quadrants or something like that to have pyramid-style approaches. But at the end of the day, you get a representation of an image. That's the whole idea, which is, has properties such that different objects live in different areas in that space, and so you can use an SVM or logistic regression or nearest neighbor, whatever classifier you want, and that typically then works well. So the key feature, of course, is to have the right representation of your local image areas. Okay, so if the right representation is what matters, then the crucial ingredient is this mapping from patches to features, and as you very well know, you can use either Sift, Hog, local binary patterns or things like that, which is what people have been doing for a long time, to get those features. Or alternatively, you can, of course, learn them. And that's, of course, just this very idea is the topic of most of the talks of this summer school, which is called deep learning, which means that you can maybe learn features of a patch and then stack a bunch of other feature learners on top of that and then get a more abstract representation and so on. Okay, so again, to set the stage for the extensions that we're going to do in a few minutes of feature learning, let's take a quick look at what those models look like. Once more, Also, just to fix the notation we're going to be using throughout. So you have pixels y, you have a bipartite network that connects these pixels with latent variable z. And in most of the models that people use, of course, the z of y, that's the hidden variables given the image, are basically a linear function applied to the patch. And often you also say that the image is a linear function applied to the hiddens. And sometimes you add a sigmoid to your hidden responses. Sometimes you add other nonlinearities and you stack them and so on. But this is the basic building block, of course. And the simplest way of learning this model is just minimizing squared error, as you see on the bottom of the slide. So the RBM is one instance of this, where you can interpret the outputs of your sigmoid as probabilities. You would then also perhaps apply sigmoids on the pixels, in which case you would assume you have binary images. You would drop the sigmoid if you assume you have real-valued images and so on. Training would then be using contrastive divergence. A different kind of model is an autoencoder. You add another layer that does the reconstruction for you explicitly, and then inference that basically stays just the same as an RBM. That's something that Mark Aurelio also pointed out yesterday in his presentation. And then squared error, minimizing squared error is just the learning principle. Find the parameters that minimize the reconstruction error, and that's it. Yet one more bilinear feature learning model is ICA, where the model looks pretty much exactly the same. The learning criterion is slightly different. You try to maximize sparsity of the hidden responses, subject to some constraint that makes sure that the weights don't give you a trivial solution. Regardless of which method you use, you get Gabors or natural images, and then you can, as I said, stack them, or concatenate them, add them or something to get your image descriptor, and there you go. That's the object recognition system. As the previous talks in the summer school showed, this works very well for various object recognition problems and so on. And one, as it turns out, useful view onto this, which is something that I assume Joshua has been talking about also in his presentation, is this manifold perspective. That is one of many views of feature learning, and why it works is that you assume that data is not occupying the pixel space uniformly, but it's actually constrained to some very, very, very low-dimensional restricted structure in that space. So the simplest assumption would be that it's constrained to some manifold, which would be the case actually if you look at images like these that differ with respect to some degree of freedom, which is in this case 3D rotation. And feature learning, what it does for you is it gives you a mapping from that space to some latent representation, such that you can represent this manifold structure in some better way. For example, having low-dimensional latent variables would do that for you. Higher dimensionals are more useful for real data because then you have lots of little snippets of manifold and so on. Okay, so this manifold perspective is something to keep in mind. I'm going to get back to that in a few minutes. Okay, if you have any questions, ask at any time. Now, brains can do much more than recognize objects, as you very well know. And not only that, many vision tasks, many computer vision tasks actually go far beyond object recognition. It's like sort of just a tiny, tiny thing, tiny aspect of vision that one might want to model. And what's really surprising is when you look across computer vision, in really, really many vision tasks, the content of the image doesn't really matter very much if you go beyond object recognition. What really matters is the relationship between images, because the relationships between images are in very, very many tasks what contains the relevant information to solve the task. And that's why most classical literature on computer vision talks about multiple views, has many eyes on the book covers and so on, and deals with the question of how you can match different parts in different images and what that means in terms of extracting structure from your data. A few examples of that are, say, tracking, of course. You have to establish correspondences between frames t and t+1 in a video. Otherwise, you can't really track an object. Stereo vision is another obvious example. When you have two views of a scene, then those two views implicitly encode depth structure. That's why you have two eyes you can extend that to more views. If you have 5 cameras looking at one scene, then if you find the right way of looking across the cameras and understanding how the views that the different cameras give you relate to each other, not what they show, but how this relates to each other, then that allows you to extract geometry about the scene and so on, which is just a generalization of stereo to more views. Optic flow is a representation that people use over and over again in all kinds of tasks in vision, and obviously this is also a representation that tells you how two images are related in some way. Invariant recognition can also be viewed as a correspondence task. You see an object and you want to recognize it, then one way of doing that is to match this object to some invariant representation that you might have in memory. And so again, this is a correspondence task, and it's not just about the image content itself. Odometry goes beyond vision, trying to map motion or visual odometry, trying to understand what the relationship is between the motion that you have undergone, maybe by walking, and the change in visual scene that can help you figure out where you are, for example, in the world, and so on. People in vision are interested in that. Action recognition is another obvious example. If you want to recognize activities in videos, you don't really care which person you see that does a certain thing. What you care more about is what the motion patterns are that you see there. And then you can even argue that even looking within images can profit from looking across different views, maybe different areas in the image and so on. Let's go back to the action recognition example briefly. Here's a little video by authors Haider and Simmel, which are psychologists that in the 50s tried to make the point that you get a very rich representation of a scene by attributing all kinds of psychological traits to the objects that you see. And I'm sure a lot of people here have seen this video recently because it's making its rounds in the machine learning community to demonstrate various things. Here I'm sort of misusing this video to demonstrate just one thing, which is, if you look at this video, if you look at any isolated frame in this video, it basically conveys no information whatsoever about the video, about the content, about the actors in there and what they're doing. The only way to get that information is to establish correspondences between frames, because the only information is really in the motion. Or most of the information is in the motion, not in any single frame. Okay. Okay, so motion, looking across images, really seems to make a difference. And the question is, shouldn't we try to model that when we do learning from data? Here's another example. So all of you know random dot stereograms. You have two images, each of which has no structure whatsoever. It's just random dots, Gaussian random noise. But if you cross your eyes and look sort of through the whiteboard, you will and bring those two on top of each other. You see that there's actually something, some 3D structure hidden in this image pair, which in this case is just a bar in the center. But again, it's images that each of which has no structure, and yet their relationship has some very strong structure. Okay, so if correspondences matter so much in vision, is there any way that we can learn them? So is there any way that we can do feature learning to encode correspondences rather than images? So for example, given two images, can we get a hidden variable z that doesn't tell us what's in each of the image, but tells us how they are related in some way? It turns out we can, and the main ingredient that we need for that is some hidden variable z that differs from the hidden variables that we're used to. We need hidden variables to act as gates, it turns out, and I'm going to show why exactly in the rest of the talk. We need a hidden variable z that can, when it's on, can blend in or blend out connections between other variables in a model. The way to implement that is to have a unit that's, for example, multiplicative, has multiplicative interactions. That's one way to get that behavior. And so if you throw those units in, I'm going to argue, you're going to sort of introduce the ability to learn relations, not just content of images. It turns out that learning doesn't really change much, luckily. So you can still use your favorite contrastive divergence, Hebbian style, or squared error minimization learning scheme. There are just a few little tweaks and changes that you have to do. And then suddenly this is a model that learns to relate two images rather than to encode one image. But the meaning, of course, is completely different than of those hidden variables because of that. Another view of these units is that a single one of these units, by having the capability of turning on and off other connections in the model, it can sort of blend in a whole subnetwork at once. So if this hidden unit is on and it's connected to a lot of other pairs of units, then as soon as this is on, the whole subnetwork is going to be in. And if this is off, then the whole subnetwork disappears again. So this can lead to a very, very different behavior of those models. And as it turns out, this is the basis of establishing correspondences. Here's a very, very brief history of gating, of this gating idea. Some of the early proposals of this were by Jeff Hinton and at about the same time by Christoph von der Malsburg, who called these mapping units or dynamic mappings, respectively. These little variables that can gate the other connections. Then shortly after that, a few years later, people were looking at energy type models, complex cell models, where you compute sums over squares of inputs. And throughout the talk, I'm going to show that these are actually doing the exact same thing as learning little mapping units. Sort of parallel line of work was higher order neural nets, where people try to learn on basis expansions. They try to square their input or something before learning, and that leads also to fairly similar behavior. Bruno Olshausen looked at routing circuits for a long time. He has been doing lots of work on this mapping unit idea that started around also in the 90s. And then later, since around 2000 or so, bilinear models became popular, which are also basically the same idea. And there were various people trying to use various training schemes and applying this to various applications and so on. The first time actually that people started to really learn these gating units from data was, as far as I know, was a subspace SOM by Kohonen, 1996. And this is basically the model that's equivalent to a subspace ISA that a lot of you know, and lots of the other gating things that are happening today. He basically did that around 15 years ago, and no one really took notice of that. And then, so as I mentioned, ISA, topographic ICA, and all these kinds of models have then been proposed a couple of years later, and they are also instances of models that somehow introduce gating connections. But they are trained from data. And only since around 2006 or so have people started to try to really take those models and plug in two images and try to utilize that to get beyond object recognition, to learn to encode relationships between images. Here's the picture from Jeff Hinton's proposal, 1981. So it's about 30 years ago, and you see those little triangle connections in there already. And it turns out now, about 30 years ago, 2011, the best performing models on action recognition problems, like on Hollywood 2 and all these other action recognition data sets, make use of these mapping units in some way. Not just in some way, they're actually a pretty essential part of these models. Without those gating connections, they probably wouldn't perform closely as well on this data. So one example is Graham Taylor's convolutional gated Boltzmann machine model that I'm sure he has been talking about in his presentation. Another example is a hierarchical ISA model that Kwok Lee, Andrew Ng, and so on did at Stanford, and that uses squaring nonlinearities, and that can also be thought of as a way to implement those this gating behavior, which I'm going to show later. Other examples are, rather than taking raw images, you can look at mocap data, also something that Graham has been done a lot. And also, you see those little triangles in there, these models, that somehow symbolize the fact that you multiply things before you send them off send them on to other units in the network. Marco Aurelio's work on gated MRFs can also be viewed as a gating type model, which is also not surprising since he also uses squaring nonlinearities. And then there are various things that you can do once you have a gating behavior. You can do things like analogy making. I'm going to go back to that towards the end of the talk. And you get invariance for free. This is something I'm going to show at the very end of the talk. Basically, what I'm going to argue is that selectivity, so trying to detect a particular motion and getting units that are invariant to that motion, is sort of two sides of the same coin. So if you learn to recognize certain motion, like a rotation or something, then you automatically get sort of for free a unit which is invariant to that motion. Okay. So this is just a very brief introduction, a very short overview of what this presentation is going to be about. Before I'm going to continue, are there any questions at this point? Okay, so then let's look at the task that we want to solve. So we have two images. We want a Z that tells us somehow how these images are related. The naive approach to this would be to say, well, why don't we just take those two images and concatenate them and then plug them into our favorite sparse coding model, put them into our RBM or something. Here's a very little sort of also naive case study that shows that this doesn't make any sense to do, that this is not something worth trying. So consider the case of, say, binary one-dimensional images, which are random, like this. And consider the transformation class between this image and the potential output image, which consists just in shifts. So these are 1D images, and say you can just shift them around to the left and to the right, or just leave them alone, no shift. So there are just 3 transformations. So what would a hidden unit have to look like if it is supposed to collect evidence for a shift to the right, say? Of course, it would have to connect to a pixel, and then in the output image, it would have to connect to its right neighbor. But since data can take various different forms, so the images are completely random or somehow structured random, or they can be noisy or something, then of course the hidden unit would have to pool over more than one pixel to get a stable estimate of what the transformation might be. So let's try to connect this hidden unit to some other pixels, say this one and this one here. And then you can sort of connect to a whole bunch of pixels and try to get more evidence for a right shift. But as soon as you do that, of course, this hidden unit actually ceases to be a detector for a right shift, because now it's also going to get very happy when, say, this pixel is on and this pixel is on, which means it would also be happy if it sees the no shift. Yes?
So insects are very good at this with their compound eyes. It seems like they have a strategy that's fairly similar to this, but it works. Can you help me figure out what I'm missing?
Yeah, I'm not sure about that work. So in insects, I know a model that has been proposed, which is a Reichardt detector. Is that something you refer? A Reichardt, so-called Reichardt detector, which actually also has multiplicative interactions in there that make this work. I would doubt that insects have a model that's really based on the concatenation like this, without any type of nonlinearity, because I would doubt that this would actually work, but I'm not familiar with that work. Okay, so the basic problem is really that the hidden units act like OR gates in some sense. They accumulate evidence from each input unit that they look at. And what you really want is something like an AND gate. There has been a nice series of papers by Christoph Zetsche who sort of really clearly laid this out, why you need those AND gates and how they really make a difference. Intuitively, in our little problem here, we want to have a hidden unit that fires if an image was shifted to the left. The way it translates to those AND gates is that, well, let's look at, say, the outer product of those two images. Let's look at this matrix here, which is each component of which contains the AND of 2 pixels, one in the one image, one in the other. Now, if you take this matrix here and make a vector out of that, and then have a hidden unit pool over the components of this vector, then this hidden unit is actually going to be able to figure out if there was a left shift or right shift, a non-shift, or whatever transformations you're interested in. And the reason is that this outer product matrix, if you think about it for a minute, is going to contain components here which only get on if the right shift was present. They wouldn't turn on if the right shift wasn't present. So for example, a right shift would be would lead to units that can be on here. So if you have a hidden unit that pools over these guys here, then that hidden unit would only collect evidence for right shift. None of these units would get on otherwise, would turn on otherwise. And the non-shift would be sort of represented along the diagonal of this outer product matrix. Only if a pixel that's on here is on here at the same position, then you're going to see a 1 here in this outer product. And so again, you can pool over all these blue guys here, and you will see, if you get a hidden unit that's able to get a stable estimate of what the transformation was. Here's a completely different view of the same problem, basically. And this is sort of more practically useful because it's going to lead directly to a learning model that we can use. So let's go back to the manifold idea, right? So you do sparse coding because you assume that data is distributed along some manifold or pieces of manifolds and so on, clusters maybe. Now, what if you have two images and they're related by a transformation class? If the transformation class is like before, a very simple one, a 3D rotation of the object, and you take an input image, x, now you start rotating it, then you're going to trace out this rotation manifold, one of which we saw in the other image before. But if you plug in another image, x, and subject this other image to the same transformations from that class, you're going to trace out another manifold, which is, depending on how similar these two images are, going to be more or less maybe parallel or close to this other manifold from the other image. And if you yet again plug another image x in here and transform it according to transformations from your class, you're going to trace out yet another manifold. So we can think of this whole setup, this whole set of manifolds that we get as a result of looking at the transformation class as a conditional manifold, basically. And whenever you plug in an x, you will get a manifold of the transformations just caused by transforming that image x accordingly. If you plug in another x, you get another manifold. So we can think of learning about transformations as sort of discovering this whole family of manifolds in the data from training pairs x and y. Okay, so but this suggests that in order to learn a model of transformations, maybe we should just learn a model of y, of the output image, just a standard sparse coding model. And how can we make it conditional on x? Let's just take the parameters in our sparse coding model and make the parameters a function of x. Right? So let's take a standard sparse coding model, an RBM, and let's just say the wjk's in there are now a function of x. Okay, let's do that. What is the simplest function we can possibly choose for our wjk parameter, which connects a pixel yj with a hidden zk? The simplest possible model is a linear one. So we want to let this wjk now be a linear function of an input image. What does that mean? Okay, if wjk is supposed to be a linear function of x, we're going to have to, for each wjk, we're going to have to introduce number of x new linear parameters which define our linear function. So the wjk of x turns into a weighted sum of the input pixels using some parameters wijk. So for every wjk, now we need a set of i's to weight all the x's to define our linear function for this guy. And of course, we can do that for all those guys in here. So we just do that for every parameter in our sparse coding model. And then we have a conditional model. Now, what's interesting about this is if we take this wjk of x now and plug it into the inference equation that we saw before, then we have the following. So the zk is, of course, just a weighted sum of the pixels inference in an RBM, in any sparse coding model. And now for our wjk, let's just plug in our expansion here as a linear function, which is sum over all I, wijk xi. And if we remove those brackets here, we see that we wind up with this expression, which says you have to sum over all pairwise products of input and output pixels and attach to each of these products a weight and sum over all of them. So do a weighted sum over all products, and that way you get your activity for the zk, and then if you want, you can apply a sigmoid or do whatever else you like to do for learning. So this means nothing other than we have to use a bilinear function of the inputs. If we want to learn a sparse coding model or a feature learning model that discovers the family of manifolds that is caused by a transformation class, it says you should use a bilinear expansion here. So similar to the AND outer product matrix that we saw before, we have to use all pairwise products of pixels and then have a linear mapping on those. Similarly, we can plug in this function parameter here into the reconstruction equation. So the pixels are a linear combination of the z, of course, and you can do the same trick, and you see that to get the reconstruction for pixel yj, what you have to do is use a bilinear model on the input image and the hidden z. Okay, so this is basically doing feature learning with input-dependent weights in some way. The simplest kind of dependency, it's just a linear function. And you can think of this also as having a sparse coding model here, where the input pixels, say these are binary, for example, where these can vote for filters to be present. So you can have an input pixel here that says, if I'm on, then I would like to see this particular filter here. And another pixel can say, if I'm on, I would like to see that filter. There's a different alternative view of this kind of model, bilinear type of model, which you get by just rearranging the nodes in this picture. This is still the exact same model. Now, if you, for example, think of your well, first of all, the parameters are now a tensor, of course, right? So for every wjk, you get your I set of parameters, so you have a wijk set parameters. So this is a 3D sort of block of parameters. If you assume that the binaries here are, if the hiddens here are binary, then you can think of the hidden, when it's on, as blending in a slice of this tensor. And what does this slice do? The slice is going to be a matrix that connects every input pixel to every output pixel. And what is that? A matrix that takes one image x to an image y. It's just linear, basically a linear model, like linear regression. So you can think of this model also as doing a mixture of linear regressors, which just map the x to the y equivalently. And if you set this up as a gated Boltzmann machine, so if you use the Boltzmann machine version of this model, it turns out that you exactly get a mixture of, in this case, 2 to the k, where k is a number of hiddens, linear regressors. Okay, so how can we learn this model? It looks slightly different from what we're used to. Well, it turns out we can learn it just in the same way that we train a standard sparse coding model. Or feature learning model, which I'm using synonymously, as you have probably noticed, because I don't think there's a very deep difference between the various different models. Okay, so the cost that a training pair, now training data is of course pairs, xy pairs. The cost that a training pair xy is going to contribute to your cost function is, if you use squared reconstruction error, which a lot of people like to do, it's just a squared error between y and the reconstruction. And for the reconstruction, you need the z, which you previously inferred using the bilinear equation you saw. But this is nothing other than basically what we've seen before. It's just a linear function applied to something which happens to be products between x's and z's, but it doesn't really change anything. It's still linear in the w, basically, if you look at the derivatives and so on. So you can write down the gradient and just do gradient descent as you're used to. The only strange thing is that your input is not a y, but it's an xy pair. But other than that, there are probably just two changes of code, 2 lines of code that change as compared to your standard sparse coding type model. Here are a few references of various instantiations of this model. One that I'm going to focus on a little bit is the Boltzmann machine version. So to get that, what you can do is, turns out, you take your energy function in an RBM, and rather than having a pairwise interaction here, you have a 3-way interaction between x, y, z's. And you have a parameter, not surprisingly, for each one of the triplets here, xi, yj, zk. And that's it. You plug that into an exp as usual and normalize. If you do the normalization over y and z and ignoring the x, if you go through the mass and you see that you just have a conditional model of these sets of units given the input. And okay. And when you do inference, so you do the math, you compute your standard inference equations, what you get is, as usual, a sigmoid applied to some linear function, and not surprisingly, this linear function is then actually a bilinear function on xy. And for reconstruction, you get a bilinear function on xz. and nothing else changes. Okay, that's the RBM. This is what you see here is the autoencoder version of that. So you can train an autoencoder and get Gabors as well. So if you want to turn an autoencoder into a conditional autoencoder, all you have to do is take your weights, which can now be different in the decoder and the encoder, take them, define them to be linear functions of x, and that's it. And so if you look at the inference, how to compute the z, you will see you get the same idea like before. This is the bilinear expansion, and you get a bilinear function here as well. And this model is still a DAG, so you can just use backprop and to train it. And if you use automatic differentiation, like in models, like in systems like Theano, you won't even notice any difference because it's going to compute the gradients for you anyway. And so this is really basically just the same thing as training an autoencoder. Any questions on that? Since every z blends in a matrix, which does sort of linear regression from x to y, from input image to output image, you can visualize them and you can look at how much does according to a given z, how much does any input pixel want to go to any particular output pixel. If you train on various transformation classes, you get plots like these, where you see how pixels are being pushed around, basically, according to the learned model. Sort of like a poor man's version of optical flow, because every pixel in this model can only go to another integer position in the image. We'll get beyond that soon, but for now it's just integer flow, basically. Here's maybe a slightly more interesting visualization of what happens when you train this type of model. Assume your transformation class is shifts, just simple shift in any random direction. What you see here is test data after we trained the model on shifts. And if you do inference, compute z, and then ask according to this z, what is the linear transformation that takes x to y, you can again look where does every pixel want to go, looking at the max, for example. The max output pixel for every input pixel, and then you can draw a little flow field like this, which says, okay, I think in this transformation here, all the pixels went to the left. And of course, the model says this because it was trained on global shifts, and even though it doesn't see any information here, it assumes, since I have never seen anything other than global transformations, I assume this must be a global transformation, global shift to the left. And then this must be a global shift to the up and upright and so on. And after you inferred your z, which is just a simple bilinear equation, you can apply the z, doing something like analogy making. You can say, for this case that you've never seen before in training, can you apply the same transformation? This just means you plug in your new x, keep your z, do your output equation, bilinear equation, and then you get this. So the model then applies this transformation that it inferred from this pair to a new image. Okay, what's interesting about this is then if you have transformations that are slightly more complicated than shifts, for example, shifts that are independent in the top and bottom half of the image, and you look at what the model thinks it saw, then it still works. And that's because these hidden units z here are factorial. And so what you will see also later is that they can specialize. So you will have hidden units that only look at the top half, others that only look at the bottom half. And so the whole thing still works if your transformations are more local, not just global. And that's, of course, important because that's what we're dealing with in reality. And we'll see that later also. Inference so far consisted in computing z given x and y, which tells you the transform, which somehow encodes the transform, or computing y given z, which means applying a transform. There's one third kind of inference in this type of model, and that is trying to answer the question, how likely are the two images that you see to come together? How likely are they instances of the learned transformation class? And that's useful also for doing invariant recognition and things like that. If you learn a conditional model like we've seen before, this actually doesn't work. You can't answer that question, turns out. So first of all, you need a probabilistic model to do that. So let's use an RBM, for example. But it turns out if you use a conditional RBM that models y conditioned on x, you can't answer that question because whenever you plug in a new x here, you will get a new RBM, basically, because the RBM is a function of x now. And that means you have a new partition function. You can't actually compare those models against each other. There's a simple trick to resolve that issue, which is rather than normalizing in the way we've seen before, you can normalize over everything, sum over all x, y, z. Now you have a model that doesn't try to model y given x, but rather we have a model that tries to model x and y jointly using the same formalism though, with gating and so on. And it turns out this is what you can use in matching tasks, but training is now a little bit more difficult. You have to use what Josh Susskind and I and various other people call three-way contrastive divergence. But I'm not going to go into detail on this just now. There's a simple hack to turn the autoencoder into a proper symmetric model that doesn't just try to go from x to y, but in both directions. And that is, you just add up the costs. So you build an autoencoder that is an autoencoder on an image y, conditioned on an image x, just as I explained before. And now you add to the cost function another autoencoder that has completely tight weights with this first autoencoder, which tries to match to model the input image x conditioned on the output image y, and now the whole thing gets symmetric, and it doesn't really matter what's left and what's right. That's also very easy to do with standard backprop and so on. Okay, so first of all, the take-home message for this first part of the talk is if you want to be able to encode transformations, not image content, what you'll have to do is compute a sum, when you do inference, compute a sum over products of input components, right? When you compute a sum over products, it turns out you get hidden z, which care about the relation, but not about what's in the image itself. Okay, if there are no questions, then I'm going to move on to the next section in my talk. Yes, there's one question. Sorry, can you say that again? If there's feature information in this tensor? Typically not. So the data that you saw here in this example, toy problem, doesn't have any structure. And so you can't actually encode anything useful about the image itself. You can visualize the W slices in that tensor though. And various people have done that. I know Bruno has a paper on there, a bunch of papers on that, where he shows basically what this looks like. And what you see then is, you do get something like a little edge type filter, which gets kind of pushed around if you go from one image to the other. So that's sort of a way to visualize this as a feature in some way, but you can't really interpret that as something that tries to encode the stuff that's in the input image. It's something that tries to encode the relationship. We're going to get back to features now in the next section because there's still a problem with these models, obviously. Yes, first, Mark.
Is there any point in making this model deep?
That's a very good question. Is there a point in making this model deep? I'm sure there's a point in making this model deep, and some of the applications that do like ISA and stuff on motion and stuff like that do use deep models. But the real difficult question is how? What do you mean by making this model deep? What should you stack on top of each other? Do you want to take this model as a module and then stack this on top of each other? That would be kind of strange, because then your next level Z's would try to encode transformations in the transformations. So in shifts, you would try to model something like acceleration or something. I'm not sure how important that is or how deep you should really go. You could imagine stacking a standard RBM model on top of the hiddens, which would sort of group together different pieces of transformations, maybe in different parts of the image, which would seem much more useful. So it's not not an easily answerable question, and there hasn't been a lot of work on trying to make these models deep, actually. Okay, so the number of parameters, since we have this tensor, is of course number of pixels in the input image times number of pixels in the output image times number of hiddens. And if you think there are lots of things that can happen in lots of transformations, then that might also be on the order of the number of pixels, or maybe even much larger, particularly maybe if you want overcomplete hiddens and so on. So you scale basically cubically with the number of pixels, say, and in your images, in a video. And that can be a problem, of course. There's a whole lot of parameters for just one simple little module. And there's a very simple, but it turns out very, very far-reaching way to reduce that number, which is going to lead us to a completely different perspective onto what it means to learn relations. And I'm going to spend the last 10 minutes here just getting into that topic, and then later I'm going to try to illuminate some of the math. It's actually very interesting behind this, what's really happening here, how these transformations are really encoded and so on. So the way to reduce the parameters is very simple. So a very simple trick that one can use. You have your tensor here with the components w, I, j, k. Let's just use tensor factorization on the parameters. Let's just say the w, I, j, k is a three-way type inner product between some vectors in some much, much smaller matrices. And let's just say the w, I, j, k is this expression here. It's just a sum over some lower dimensionality of some vectors. This is known as a parafac factorization. We could have used any other matrix tensor factorization in order to reduce the parameters, but this is one thing one can use, and it's probably the most simple thing one can use. If you do that and you plug your newly defined wij into your inference equations, something very interesting happens, which is the following. So we recall that zk is a bilinear function with parameters wij. Now let's plug in this expansion here, this tensor expansion for our wij, and let's push some terms around here. Let's group things that depend on x, and let's group things that depend on y. And if we do that, then we see that we get this expression here, which says to do inference, to compute z given the two images, what you have to do is build a linear combination of a bunch of products. And the products, each of the product terms here, is just a filter applied to an image, right? So you have to linearly project the x, you have to linearly project the y onto some features, multiply them together, and then compute a weighted sum of that. That's going to give you the hiddens. So the picture associated with that is this, right? So you have your input image, projected onto a bunch of filters, take the output image, project it onto a bunch of filters, and then let hiddens compute a sum over products of filter responses. It's very similar to what we had before. We had hiddens computing the sum over products of pixels. Now we have hiddens computing the sum over products of filter responses. But the number of parameters is, of course, much smaller here. Now, the interesting thing is that what happens here is that you apply filters and then you multiply the filter responses together, right? So you try to match filters, basically, match filter responses. And if you plug the same expansion into the energy function of an RBM, you get something very similar. You end up with products that multiply filter responses together. And the model doesn't really change. Inference doesn't really change because this is just an expansion that you can do and undo whenever you like in your code. And so learning stays basically also the same. Yes, there was a question?
This seems like the crux of the issue. Can you give a simple example?
An example of?
The concept you were just outlining, the filter match.
Okay. We're going to see some examples of what the filters look like after you train this type of model. For now, all we did is factorize our tensor, so we reduced the number of parameters, and then realized that doing this is equivalent to having a different model with a different inference equation, which works like this, which says, now to do inference, what you have to do, project onto your basis functions and multiply them together and then sum them. Yes? How much freedom you have in the tensor factorization? Yeah, so it's completely under constraint. So you have lots of freedom. Like you have in any neural net that you train, there are lots of symmetries. There are lots of different equivalent ways of doing that. And when you learn these models, you basically ignore that. Basically, this turns into a slightly deeper neural net if you think of this, if you train this model. And the way I'm dealing with this is just ignoring the fact that there are many equivalent solutions and stuff like that, and there are local minima and so on. Sorry? Okay. Okay, so you can do that to the RBM. You can do the same thing for the autoencoder. And the autoencoder, the whole model gets somewhat simpler, even though it looks more complicated. You take your autoencoder, which tries to encode y, say, and now you have to make sure that all the parameters in here are gated. But so before doing the gating, you project both y and x onto filters. So this is what the model looks like then. And so project x onto filters, project y onto filters, have a layer that computes products between corresponding filter responses, and then let hiddens just compute sums over those products. This is just one half of this RBM factored model that you saw before. And then you just have to add a decoder that does the opposite. It just undoes the whole thing. So you just continue on and do the exact opposite. This is still a DAG, and you can still train it with just gradient descent and backprop. And Theano, you factorize your WIJKs, and you won't even notice that there's any difference. So it's going to compute gradients for you and stuff like that. So there's nothing really complicated or magic behind this. What's interesting though is when you start training this type of model on actually transforming images, and you look at the filters, then you see that they really try to do something very sensible. So here's an example of two random images, like in the example we saw before. There's nothing in those images, randomly drawn binary pixels. But obviously there's structure in the way they change, because these images are just shifts. And so we have a whole set of images, like 100,000, which are just shifted around. And then if you look at the filters on the input image, they turn into a Fourier basis, basically. And if you look at the filters that you apply to the output image, you also get a Fourier basis. And interestingly, the transition between them is a phase shift. So you learn the filters that you end up multiplying usually have the same orientation and same frequency. They just have a different phase. And it has been long known that the most natural representation of a translation of an image is really the Fourier basis. But this is something the model just figures out by just seeing transformations, seeing shifts. And it decides that the filters it wants to use to represent the shifts is the Fourier basis. What exactly this phase shift means is something I'm going to go back to in the second half of the talk. Can actually very concisely describe why you need those phase shifts and what they exactly mean. You can analyze those. You see that you cover all kinds of orientations and frequencies and so on, and different phase deltas. You get hiddens that are tuned to velocities and stuff like that. I'm going to go over for now. You can do the same experiment that we did before with the half image translation, where the top half of the image shifts independently of the bottom half, and then you get filters that specialize in either the top or the bottom half of the image. So a hidden unit that looks at this product here is going to ignore the top half of the image, and here this filter ignores the bottom half, and so on. So if you have local transformations, then you just ignore everything except for a little part in the image. If you, instead of shifting images, you apply random filters, you convolve the image with random filters, you also get a Fourier basis, and this means nothing other than the model sort of discovered that if you want to do a convolution, you should do an FFT. The natural representation of that is, again, a Fourier transform. Right? So convolution is most naturally expressed in the Fourier domain. And slightly more interesting is when you train on rotations, then you get these filters that looks like radioactive signs and things like that. And they're also phase shifted in some sense. It's not as obvious what phase here means in this case. But actually, it's not surprising that you get these types of filters from rotating images. They are also a very natural basis. And there are people who have looked actually at rotation invariant recognition. They use these kinds of swirly filters. But here again, the model just figured that out by seeing random dots rotate around. And then finally, before I'm going to stop the first half of the talk, is when you train on natural images, natural video that you crop from TV data. If you just let the model watch TV and just train it and look at it, you again get a Fourier basis, which says your transformations are sort of dominated by shifts, which is due to camera shifts and maybe stuff like that. What's interesting, if you drastically increase the number of filters and you whiten your images before you learn, you get a basis that looks like this. So you get a Gabor basis for every frame, and they also phase shift. And so this is sort of the extreme case of this half split screen shift that I showed before. So a natural video can be thought of as being composed of lots of little shifts. So in some part of the image, some little thing moves around. And the way that the model encodes this, of course, is by having lots of little Gabor functions that are phase shifting from one frame to the other. And OK, so finally, if you apply this to natural videos, as I said in the beginning, you get fairly good performance on various data sets. And what is still a little bit of a mystery is how these phase shifts occur, what they really mean, why do you get these swirly filters for rotation, and what can you actually do with that. And the whole math behind that is something I'm going to explain then in the second hour after the lunch break. And things you're going to learn then are things like what it means to have shared eigenspaces. You're going to learn what a quadrature filter pair is, in case you ever wondered. And then I'm going to discuss some of the applications and extensions of that. Thanks.